Okay, welcome back. So what we wanted to, what we did last time is to talk about signs of permutations. And this was defined to be in some sense you first take the number of crossings of the permutation, which could be pictorially read off from the crossing diagram or tangle for the permutation, and then if it is even, then you declare the sign to be +1, and if the number of crossings is odd, you declare the sign of the permutation to be a -1, okay, also called even and odd permutations. Now I wanted to do a few more examples of these. So let's try and find signs of cycles. So here's two examples. So if you take n to be 4 and you take the permutation pi to be the cycle 1 2 3 4, so which I will write first in 2 line notation, 1 going to 2, 2 going to 3, 4 1. So this is the cycle written in 2 line notation. And also notice that the other notation for permutations that we looked at is what we call cycle notation. So in cycle notation, the same permutation would be just represented by the 4 numbers 1 2 3 4 written in brackets. Okay, this is to be thought of as meaning 1 goes to 2, goes to 3, goes to 4, goes back to 1. Okay, so what's the sign of this pi? So that's the question. So let's draw the tangle diagram for pi. So 1 maps to 2, 2 maps to 3, 3 maps to 4, and 4 maps to 1. Okay, so here's the tangle diagram for pi. This satisfies all the rules for drawing tangle diagrams correctly. So the number of crossings is 1, 2, and 3. So the number of crossings this case is 3, and so the permutation pi is odd. Now similarly, of course, if you drew a permutation, the diagram for the 5 cycle, so I take pi to be, now I'll just use cycle notation, 1 goes to 3, goes to 4, goes to 5, goes to 1, and again imagine drawing the, so here's the tangle for this, 2 goes to 3, 3 goes to 4, 4 goes to 5, and 5 goes back to 1. And now the number of crossings is 1 2 3 4, so there are 4 crossings, and therefore this permutation now is even, okay, because there are 4 crossings here. So from this it's kind of clear how cycles behave. If you have a cycle of even length, say 1 2 3 going on till some even number, then that permutation would have sign -1, and if you have a permutation a cycle with odd length, say going 1 through 5, then that would have even number of crossings, and therefore it would be an even permutation. Now here's a slightly more general example. We'll still look for a 4 crossing, but we'll do this with let's say n equals 7. Okay, so what does this mean? So let me take my example. So let me take sigma to be the following. It is a 4 cycle with signs 1 to 3 to 5 to 7, and then it leaves the remaining numbers as it is, 2 4 6. Okay, so here's the permutation sigma written out in cycle notation. So recall, what does this really mean? So let's draw the tangle diagram for this. So let me first draw 1 3 5 and 7. So here's 1 3 5 7. So what this permutation does is, well, it is a 4 cycle if you think of only these numbers 1 3 5 and 7. So 5 goes to 7 and 7 maps to 1. Okay, so that's the diagram if you only looked at the numbers 1, 3, 5 and 7, and the number of crossings here is of course the same as the number of crossings in the other 4 cycle that we drew. So there will be 1, 2, 3. So there are exactly 3 crossings, okay, as far as these 4 numbers are concerned. But of course we still need to throw in the other numbers. So for instance there is 2, 4 and 6. Now what this permutation does is it maps 2 to 2. So I just need to draw a straight line which joins 2 and 2, just taking care to ensure that the rules for tangles are preserved. So for instance I don't want to have 3 things passing through a single point. So when I join 4 to 4, I just need to take a little care to ensure that it doesn't pass through the same point. So similarly 6 to 6. Okay, so here are the 3 extra curves that you need to throw in: 2 going to 2, 4 going to 4 and 6 going to 6. Okay, so now in addition to the 3 crossings that you already had amongst the lines which joined 1, 3, 5 and 7, what we now have are, well, a few more lines, a few more crossings. So let's count the number of crossings. So observe that the red line which joins 2 to 2, it accounts for 2 crossings because it meets the line joining 1 to 3 as well as the line joining 7 to 1. So there are 2 crossings. The red line which joins 4 to 4 again accounts for 2 crossings. The red line joining 6 to 6 again accounts for 2 crossings. Okay, so the total number of crossings is, well, how do we count the number of crossings? So the number of crossings is therefore the following. There were 3 original crossings plus the crossings that come from the red lines. Well, they look like 2 times, well, each of those red lines contributes a 2. So it's 2 plus 2 plus 2, 1 for each red line. So this is the crossings involving the red lines. Okay, and these are the crossings that only involve the white lines. So these are crossings that don't involve the red lines, so not involving the red lines. So I should say these are crossings that involve at least one red line, so involving a red line. Okay, so you count the crossings in these different ways. You look at the crossings in which at least one of the 2 curves is a red line, that's counted by this, and then you look at the crossings in which you don't think about the red lines at all, only look at the white lines. And so since we are only interested in whether or not the number of crossings is even, so observe that the number of crossings in this case is still odd, because it really only depends on whether the original number of crossings was even or odd, the number of crossings not involving the red lines. Okay, so this turns out to be the general phenomenon. So if you wrote down a permutation like this, so a permutation like a sigma here, you would often also call this a 4 cycle. It really only permutes these 4 numbers in a cyclical fashion, it doesn't do anything to the other numbers. So when you have a permutation like this, the sign of this permutation is just the same as the sign of the underlying 4 cycle, okay, which is it's an odd permutation. Or if say this were a 5 cycle and these were all being mapped to themselves, the sign of this would just be the sign of that 5 cycle portion. Okay, so this observation here is sort of it's very useful. So the number of crossings is odd, therefore the sign of sigma is in fact -1. So let's just do a more complicated example now, which tells you how to put 2 different cycles together. So let's take this example now. Again, let's take n equals 7. Let's take a permutation which maps 1, 3, 5, 7 to themselves, but let's now do 2, 4, 6 also map cyclically amongst themselves. Okay, so it's this notation here, remember, means that 1, 3, 5 and 7 form a 4 cycle, and then 2, 4, 6 amongst themselves form a 3 cycle. Now the question is, what is the sign of such a permutation? Okay, of course conceivably what one could do is to try and count the total number of crossings. We could look at draw the same sort of diagram in which you would have a 4 cycle and then a triangle diagram for a 3 cycle, but then they would all be crisscrossing each other in a rather complicated fashion. So instead of sort of just counting it by brute force, here's something that, well, okay, here's the question. So here's the key observation that we will use to simplify this calculation. So here's a key observation. You can think of pi as really being the following. Pi can be thought of as being the composition of two permutations. So remember, we talked about the composition of permutations. So this is sigma 1 composed with sigma 2. Where, well, what sigma 1? Sigma 1 is the permutation that we just wrote out, 1, 3, 5, 7, the 4 cycle, in which the remaining 3 are unchanged, and sigma 2 is the 3 cycle, 2, 4, 6, with 1, 3, 5, 7 unchanged. Okay, so the key observation is that you can now use this notion of composition that we talked about and obtain the given permutation pi really as a composition of two simpler pieces, one being sigma 1 and the other being sigma 2. Okay, so I leave this as an exercise for you to check that in fact the composition of these two permutations does give you back the original permutation pi. So now we go back to this whole business of sign and the relationship of sign to composition and so on. So recall from before, the sign function is really multiplicative with respect to composition. So if I had sigma 1 compose sigma 2, the sign of the composition is just the product of the two signs. Okay, so this is really the the important reason why compositions are especially suited when you want to try and understand signs. If you can write your original permutation as a composition, then the sign is just a product of the signs of the individual constituents. So here it's just a sign of pi 1, sigma 1 and sign of sigma 2, but observe we've already talked about how to understand the sign of sigma 1, okay, and that's exactly the thing that we wrote out here. Sigma 1 is really the permutation which cyclically permutes 1, 3, 5, 7 and does nothing to 2, 4, 6. So it's the sign of sigma is really just the sign of whatever this 4 cycle part is. Okay, the things which map to themselves, the red lines so to speak, always contribute an even number of crossings. So they don't really contribute to the sign of the permutation. So the sign of sigma 1 would really just be the sign of the 4 cycle, so which is -1 as we said, and similarly the sign of sigma 2. So notice sigma 2 in our definition was just the 3 cycle 2, 4, 6, and in which the remaining just map to themselves. So they are sort of like the red lines in our picture. They will contribute an even number of crossings, and we only really need to worry about the number of crossings between which only involve the lines joining 2, 4 and 6. So here it's a sign of the 3 cycle 2, 4, 6, which is a +1. Okay, and so putting these together, the sign of the original permutation pi is just the product of these two signs, therefore it's a -1. Okay, so here's a way of really understanding signs by making full use of this whole of composition as an operation. So and finally, using this business, here's the last thing that would be nice to do in this business. If you have n, let's say a natural number, let's do the following: total number of permutations of n, remember, is just n factorial. So for n equals 4, for instance, so recall this old table that we talked about, the notion of cycle types or cycle structure. So the various cycle types that we talked about, you can have a 4 cycle, or you can have a 3 cycle and a 1 cycle, you can have a 2 cycle and another 2 cycle, 2 cycle and 2 1 cycles, or 4 1 cycles. These are the various possible cycle types when you are trying to permute 4 numbers, and the number of permutations of each type. So the number of permutations of each of these cycle types we had worked out before. It is 6, 8, 3, 6 and 1. And finally, since we talked about signs right now, it's natural to wonder which of these permutations are odd and which are even. Okay, so we could ask which of these permutations are odd and which are even, and we already have the techniques to answer these questions. For instance, a 4 cycle, okay, if you have a permutation which is just a 4 cycle, we just talked about signs of cycles, a 4 cycle is always odd. Okay, so I'll just write -1 for odd. Now if I have a 3 cycle together with a 1 cycle, so we again just did this, when you have say a cycle decomposition, it's a product of 2 cycles, you can think of it as a composition of 2 permutations, and so it's just the product of the signs of each of these guys. So a 3 cycle would be even and a 1 cycle would be even. A product of 2 evens is again even. So this is a sign +1. Similarly here we do the same thing here. There's a 2 cycle composed with another 2 cycle. A 2 cycle is odd, another 2 cycle is therefore also odd. So a product of 2 odds, odd permutation is an even permutation. Now here a 2 cycle is odd, 1 cycles are both even, so odd times even will still give you an odd permutation. And finally, each of these ones is really a even permutation. So this is the full list, which of given a cycle type, is it odd or even, and the answers are right there. So let's count the total number of odds and total number of even permutations. So which of these are the odds? Well, the first row, there are 6 odd permutations with cycle structure 4. There are another 6 odd permutations with cycle structure 2 1 1. Okay, so between these there are 12 permutations with 12 odd permutations, and the even permutations are, there are 8 of them with cycle structure 3 1, 3 of them with cycle structure 2 2, and finally 1 with cycle structure 1 1 1 1. So these 3 together again gives you 12. Okay, so there are half the number of odd and half the number of even permutations. Okay, and this is in fact a statement which is true in general, that n factorial divided by 2 permutations would be even, and the remaining n factorial by 2 permutations would be odd. Okay, so it's probably a nice exercise to try and prove this fact, that in general half the number of permutations are odd and the other half are even. So let me just state this as a problem prove that the number of even permutations is n factorial by 2. Okay, and another exercise is to try and work out this table that I just did for n equals 5. Okay, so here's another exercise problem that I'd like you to try out. Is to work out this table. So write down the entries of this table for n equals 5. So the same table that we just drew. Okay, write out all the possible cycle structures for n equals 5, and for each of them work out the number of permutations with that cycle structure, and also work out whether that permutation would be an odd permutation or an even permutation, and from that conclude that at least see that half of n factorial, so 5 factorial in this case is 120, so you should get 60 even permutations and 60 odd permutations in all. Okay, so next time we'll talk a little bit more about permutations.